DKIM that are exploited remotely without any setup published anymore today, and most vulnerabilities are in Internet Explorer whatsoever. So Nepenthes was cool like 2 years ago, where everything spread through DKIM, and nowadays we need to actually find the exploits. So the attacking hosts aren't coming to us anymore. They're not knocking at our door and saying, I want to attack you. But instead, we have to spider the web and find a malicious website. And this is what this software does. So it's not released yet because there's still some work in progress being done on it. And it's written in Python, mainly by Jose Nazario, who is working for Arbor Networks. And we're collaborating on this. So it spiders the web like a search engine looking for attacking sites. And to find actually attacking sites, what we do is we deobfuscate all this JavaScript, which is often pretty much obfuscated, and then again just run the libemu shellcode detector on it. So yeah, if there is an exploit in this JavaScript, there's going to be some variable holding the actual shellcode used in that exploit, if it's not like cross-site domain, cross-domain scripting vulnerability. And for these, there are static modules detecting these kinds of vulnerabilities, similar to Nepenthes. And this way, we can find malicious websites. And as you know, there's already high interaction client-side honeypots, and this is an ideal pre-filter because running each site on the web through a high interaction client-side honeypot takes like, I don't know, one minute per site or something. And using this, we can spider the web really fast, and suspicious URLs can be then forwarded to a high interaction client honeypot, speeding this up a whole lot. So we want to make this even cooler by downloading the malware automatically from these sites instead of feeding them to a high interaction honeypot like we do in Nepenthes right now, because with libemu we already have the capability to see what is the shellcode actually doing, and if we have this capability to see what it's doing, why not download the malware directly in the low interaction honeypot? And this would then be a real cool thing then, because it's very fast and gets you all the malware. So how does it work? We have a URL, we fetch the malware on all reference resources. We deobfuscate the included JavaScript, which is often like several nested eval commands for those of you who know JavaScript. Then we just run it through libemu or look for certain cross-domain scripting vulnerabilities like in the old ages of Internet Explorer and something like that. And this is actually from a very recent Internet Explorer exploit, where it just has a shellcode, which is a Perl script, which has a shellcode, but then it writes a JavaScript file, which then calls just an unescape on the shellcode. So in the end, you will just have the actual shellcode as a parameter to the function in JavaScript, and using SpiderMonkey, we can just look at all variables and parameters, and then use libemu to see, okay, this one is a shellcode, this is what we are interested in. Another way of finding malware besides the Honey client is just a spam thing, because like at least since Stormworm and even before, a lot of malware is just spammed around, and dumb users click on attachments because it's a funny picture or something, or dancing skeleton, and execute it, and well, this is malware interested in too. So what we do is just we set our own up our own mail server. Propagate email addresses to this mail server all on the web, like on some forums or whatever. And then just, well, this is like dark space for IPs. This is like dark space for mails. So we just consider all email coming to this mail server as malicious. And as a result of this, all executable attachments to this web server are malicious too. So this is the way we can very simply collect these kind of malware. And yeah, this is nothing to be released because there's no real software being developed. It's just setting up your mail server and scanning through all attachments. That's another thing we're doing. And now we've got that huge pile of malware, which was actually what we did in the first year. We just stacked up the malware, and we're happy we had so much malware. But we want to put some use to all this malware we were collecting. So we're doing some malware analysis. We're working together with the folks from the TU Wien here in Vienna. They developed the Anubis sandbox, which is pretty simple. It's just like a kernel rootkit running in a virtual machine. So you load that malware into the virtual machine. This kernel rootkit records all calls to APIs and therefore knows what the malware does. So yeah, what you get in the end is a detailed report on what the malware does. So what we are especially interested in is like this here joins IRC network, and this is just the header of the whole page. So it goes like 20 or 30 pages long, and then we can see the detailed information where it's connecting to, which works for, at the moment, not so many IRC binaries, but it works at least for some. So this takes the burden of manual analysis away from us. Yeah, and then we got these reports, and we wrote some parser script for these reports, and what we get in the end is just a huge database of botnets. So we have a binary here, and here's the botnet. So this is actually botnet command and control host. Here's the part, no server password. This is the channel with the channel key, the server nickname, username, and real name. And this goes on for, this is just like, I just attached to the screen where this analyzation script was running and then copied it. So as you see, for some binaries there's also no botnet information, but it's just a whole lot of botnet samples we're seeing, and yeah, we just fetch it out of them. And yeah, well, that's about it for getting all the botnet information, which we are going to use later. And another problem in malware analysis we were running into was polymorphic binaries. So for those of you who know the all-APL worm, it's polymorphic. So each attack yields to a new binary with a new unique MD5 sum. And that's pretty nasty because this is a screenshot from the web interface, which was just displaying the most recent binaries. And as you can see here, these all just hit our sensors once. And these were all APLs, and these just pollute our database because, you know, it's pretty hard to work with a database where you're seeing like, okay, there's like 100 new binaries today. What does this actually mean? Was there 100 new botnets created today in one single day, or was it just one polymorphic binary attacking you once again? And what we did is develop a custom hash function, because there's a lot of nice algorithms to group malware binaries into specimens, for example, VX class, but these probably take like 10 minutes per binary. Again, this is taken from VX class, which is a great thing, but we get at peak times 10 binaries per minute, and this is, well, doesn't match by a factor of 100, so it's too slow by a factor of 100. And we need a way faster method to actually group binaries together into specimens. And what we do is we look at the actual PE structure of these binaries, and we developed a hash function that just inspects the PE headers. And therefore, polymorphic binaries always share the same basic PE characteristics, and this way we can identify them and group them together by this specific hash function, hash value in this case. So we hash the PE header, and yeah, we can group them by the hash value as if it was the MD5 value of the whole binary. So we can say this is one malware specimen, this is one malware signature name or whatever. And it's important to note that the result of this research is a hash function and not a message digit. So it's very trivial for an attacker to construct two binaries which entirely different content which share the same hash value, because it's a hash function and not a message digit. This is a cryptographic difference. So first, security by obscurity applies. So if we tell attackers how our hash function works, they can just construct collisions and therefore circumvent our research. And we must be very careful when publishing these hash values. So when we say we have a new malware specimen with this hash, this might have some consequences. So it's better to MD5 the actual hash value again. So an attacker cannot reverse the hash function to the PE properties. Yeah, and this hash implementation is made by me, was my research, and if there's some interest, yeah, please.
A small question, why don't you use MD5 in the first place for hashing then?
Well, we actually do, but so for the web interface, we actually use MD5 hash because the hash function is very long and we compress it that way. But the actual hash function itself is very, I just wanted to say that it is easy to create collisions this way. So we must make a secret of our hash function to prevent collisions. And yeah, what we first look at is the actual subsystem or whatever, the stack size and the imported libraries. These are global PE properties, and these are very specific sometimes. In other cases, stack and heap size is constant for certain compilers. So these are just some basic measurements, and the more interesting things we are looking at is the properties of the actual sections. So if you don't know PE files, so for those who don't even know that, PE files are the executable file format of Windows. And like ELF is for Linux. And we're looking at data section and code section and the like. And we are actually only looking at the first 3 sections because otherwise the hash wouldn't have a constant length. We look at the size of the sections in the executable, where it's going to be loaded in the memory. These are very different for each binary. We XOR the hash names. For some compilers, we XOR hash the names of the sections. For some compilers, these are static. For other malware specimens, these are dynamic with each instance. With each specimen, not with each instance. And what is very important, because we still had some collisions for different specimens, is we approximate the Kolmogorov complexity, which is a theoretical measurement in computer science for the richness of information. So if you want to say 6As is way simpler in the richness of information terms than this random string, then you do this by Kolmogorov complexity. And to approximate this, because from definition this cannot be generically computed, we approximate it by compressing the data and then just look at the ratio of the compression, which is a good approximate of the richness of the data, because if you have a lot of A's, one like 4 kilobytes of A's, you can compress it to a few bytes. And if you have 4 kilobytes of random data, you can't compress it at all, more or less. And this is our approximate of the richness of the data, which we scale down to an index between 0 and 7. And this way, we can easily say, for example, this is code, or this is some zero initialized data or something like this. And the funny thing is, even if we have a metamorphic malware specimen, which transforms its code, each which is even worse to detect than polymorphic malware, the richness stays the same. Even if all instructions change, the richness more or less stays the same. So this is a very good measurement for this. And the results from real life showed us that this hash function we developed actually works, because there's 33 distinct PE hash for all APLs we ever see. And for all these PE hashes for these all APLs, we have exactly 0 collisions with any other kind of malware. And 3 of these hashes were holding more than 99% of all APL, which correlates with 3 different all APL variants discovered by various antivirus companies. And our guess is the remaining 30 hashes, which all were only holding 1 binary, were transfer errors. So there's like 20,000 all APL we've seen so far, and they all have the same hashes except for 30, where we're saying these are simple transfer errors because they have pretty unusual sizes, and some aren't even valid PE files. So this showed us this actually works, and what we have now is this nice grouping of binaries. So as you can see, we now have those with more hits again, and we can group them together and take out all these all APL and such, and so it actually works. And now that we have all the data, we have analyzed the malware and have got some botnet information and whatever, we want to do some botnet monitoring, because most of today's DDoS still comes from botnets, and so we want to be seeing which botnet herder is attacking whom, or where are all these phishing mails coming from, and all the like. This is mostly today coming all from botnets, so we do some botnet monitoring. And yeah, we have developed a tool, botsnipd, for the German Federal Ministry of Information Security, I guess is the correct translation, so it's a BSI for the Germans here.